Okay, so when we look at empirical formulas, we're going to be dealing specifically with covalent compounds, okay, not with ionic compounds, because ionic compounds we try to reduce all the time. Okay, covalent compounds we don't necessarily. Okay, so this is looking at a covalent compound, and we're going to be able to determine its smallest whole number ratio of that particular basically combination. Okay, so I want you to look at page 245 and read just a little bit about empirical formulas on that very first paragraph. Okay, so I want you to go ahead and read that very first paragraph on page 245 to kind of introduce to you about empirical formulas. So steps for empirical formula. We want to start, or we usually start with a percent composition. Okay, that's usually how these problems start. If they start in grams, that's great. If it doesn't, we're going to put them in grams. Okay, and I'll show you how we do that. But most of the time, we begin these with a percent composition. So it might say it's 38% carbon, 42% oxygen, and 20% hydrogen. Okay, that could be the percent composition of this particular compound. Okay, these numbers are made up, so it's probably not going to work. But I'm just telling you that's what we're going to start with. Usually we'll start with a percentage. If that's the case, we want to put these percentages in grams. So this is our step 2. Okay, change percent to grams. And there's a really easy way that we do this. Okay, when we're given a percent composition, we're not usually given a starting amount. So we just know basically either we're looking at 2 molecules of it or we might be looking at 2 million molecules of it. We don't know. It's just a percentage. So the way that we do this to make it easy for ourselves is we just assume we're working with 100 grams total, just like 100%, which would make this, we're working with 38 grams of carbon, 42 grams of oxygen, and 20 grams of hydrogen. Okay, so we start with a percent, and then we just convert right to grams. Okay, remember, this is made up, so this doesn't form anything real. I'll start with a real example here in a second, but that's just how we convert it. So we start with our percent composition, and then we will convert those or just change them right to grams. Okay, does that make sense? All right, good. Is convert grams to moles. For each element. Okay, so convert grams to moles. Step 4 is divide each element, right? And that's the number of moles. So divide each element by the smallest number of moles. What this does is this gives us the ratio of elements to elements, okay? So it's going to give us the ratio, and we should come out usually with whole numbers when we do that division, okay? We'll show what happens if it doesn't come out a whole number. But what this step does is this gives us the ratio, okay? This gives us the ratio of elements. I'll put that in there, okay? So if we have, our calculations come out to 0.5 moles of carbon and 1 mole of oxygen, we would divide each of those by the smallest, and we would have a 1-to-2 ratio of carbon to oxygen. Okay, we see that kind of relationship. The only way that we like to compare quantities using or within elements has to be mole to mole, right? We can't compare grams to grams because the molar mass is so different of some elements. So the only way we can compare those is moles to moles. Okay, so make sure everything gets in the moles first. Okay, last step here is the easy one. Okay, and the last one just is build the compound. Okay, so we've got our ratio, then we just build the compound. Okay, and these are empirical formulas, so these should be the smallest reduced version of these compounds. Okay, so we're going to start with an example here. Okay, and we're going to start with its percent composition. This happens to be 78.1% boron and 21.9% hydrogen. Okay, and this one is in your book. We're following along right with the one in your book, so if you'd like to follow along there, you can, but we're going to do this whole one in class together anyway. Okay? So we've got it in percent composition. That's what we're used to starting with. What's our first step here? Change to grams, okay, which means we're going to start with 78.1 grams of boron and 21.9 grams of hydrogen. Okay. Okay, so I'm going to convert here 2 moles. Moles gets the 1. What's the molar mass of boron? 10.8. Okay, and I want to leave that decimal because that's not close enough for me to round. Okay, so we need calculators and periodic tables out today. I'm sorry if you don't have those. Tell me one more time. 4.2. Okay, so in this sample, I've got 4.2 moles of boron. Okay, my hydrogen conversion is going to be pretty easy, right? Grams to moles of hydrogen. What's the molar mass of hydrogen? 1. Okay, I'm going to even leave that there. Okay, which gives me 21.9 moles. This doesn't seem right. 4.2 does not seem right to me. Try 78.1 again, divided by 10. I didn't look at that very closely. We should have a higher number there. 7.2. I'm sorry. Okay, there we go. Okay, yeah, so that looks a little bit better. 7.22 moles and 21.9 moles of hydrogen. So we've got both of our elements in moles. The next step is to do what? What's our next step tell us to do? Good. Divide each element by the smallest. So when we do that, one of these should come out to a 1 ratio because you're dividing it by itself, right? The smallest one you're dividing by itself. So which one of these is smaller? 7.2. So I'm going to divide this one by 7.22, which gives me 1 for boron. I'm going to divide this by 7.22, which gives me what value? 3.0. So we're going to round that. We want that to be a whole number. Okay, most of the time we want it to be a whole number. So it gives us a 3. So now this gives us the ratio between these elements. So we've got 1 boron to 3 hydrogens. Okay, so when we build our compound, now we just call it BH3. So that is the smallest ratio, the empirical formula of a compound that consists of 78.1% boron and 21.9% hydrogen. Okay. If we look at just those percentages, it would seem as though there's going to be more boron molecules, right? Because it's 78% boron. Why is that not the case? Why is there not more boron atoms? Exactly. It has a higher molar mass. It weighs more. Okay, so of all of the mass of that compound, boron takes up the vast majority of it because hydrogen is so light. Okay, so we've got 3 hydrogen atoms, 1 boron atom. Okay, questions here? Let's name that molecule for fun. For fun. Okay, first of all, ionic or covalent? Covalent. Covalent. Okay, so that means you use prefixes or you don't? You do. Okay, so what is it? Boron. Hydride. Hydride. Hydroxide is OH. Remember, hydroxide is OH, so it's got to be that polyatomic ion. Okay, and hydroxide will be just, hydroxide will be ionic compounds. Okay, so this is boron trihydride. Okay, let's try another one. What is the empirical formula of a compound that contains 89.14% Au and 10.8% oxygen? What's Au? What element is that? Gold. Good. Okay, so first thing that we do is we take our percents and we just change them to grams, right? We assume we're using 100 grams of that substance. So we're going to start with 89.14 grams of Au and 10.8 grams of oxygen. I like to leave in that little space in between. That way I can just make my T-chart right there. Okay, so I want to go grams of Au to moles of Au. Okay, so when I want to get rid of grams, where does it need to go? Good, on the bottom. And I want to go 2 moles. Molar mass of gold. We can round that up if you want. 197. Okay, and then when we round with oxygen, we want to go from grams of oxygen to moles of oxygen, and oxygen's molar mass is 16. Okay, let's go ahead and divide by our smallest, which is 0.452. Okay, so divide by 0.452 should give us a 1. If we divide by 0.452, we get 1.5. Is that going to work for our ratios? No. Can we just round up to 2? No, we can't. Okay, we only round if it's really, really, really close. So will this compound work? Au 1.520? No, probably not. Okay, so what do you think our solution might be here? Okay, scale it, kind of, yeah. We're going to take this whole thing and we're going to multiply it so 1.5 gets to a whole number. So what would we probably multiply it by? 2. Okay, so we're going to take that whole thing. So that means our ratio would be Au3O2. Backwards. Sorry. You're right. Backwards, sorry. I'm backwards. Okay. Wow, it's not my day today. Okay? So if we lined it up like this, it would be AUO 1.5, which doesn't work. And then we'll multiply that by 2. That's my fault. Okay, so that leaves us with AU2O3. Okay? And then a way that you can check yourself once you do that is to just do the percent composition again. Right? And as long as you come out with this right percent for each of those, you're good to go. Okay, so you could find the percent composition of oxygen by taking 16 times 3, because we've got 3 of them. So 48 divided by the total, which would be 442, I think. Okay, so 48 divided by that gives us 10.85% oxygen. Okay, so you can check yourself by just using that percent composition again. Does that make sense? So this was just to check. Now we have 4 elements instead of just 2. Okay, so does that change the process? No, same process, just a little bit more work. Okay, so you can go ahead and try this one on your own if you want. I'm still going to work it up on the board if you get stuck. Okay, please ask questions if you need that. Okay, so we were already given grams, so we don't need to necessarily convert to percent composition then back to grams. So start with your number of grams here. If we start with an empirical formula, let's say HNO3, that's my smallest number that has that percent composition, right? That's the smallest ratio that has that composition. A molecular formula for this compound might be this, H2N2O6 or H3N3O9. Okay, do you see what I'm doing there? Yeah, we're just increasing the basically the number of atoms in that compound. We're not changing the ratio; it's still 1 to 1 to 3, but we're increasing the size of that molecule. Does that make sense? We're making that a larger molecule. So this is the empirical formula. These and anything else with that ratio would be considered a molecular formula. Let's see. So here is how we would decide basically or convert kind of between those molecular formulas and empirical formulas. Okay? So once we have our empirical formula, we're going to find the molar mass of the empirical formula. Okay. And when we're talking about empirical formulas and molecular formulas, they might ask you questions that look kind of like this. They would say, this is the empirical formula, CH, yet this compound has a molar mass of 348. Okay, what's its molecular formula? Okay, so it might give us the molar mass of this larger compound, and it might give us the empirical formula of that compound, and we have to decide how much bigger did that molecule become. Okay, at what kind of rate did we increase the size of that molecule? Does that kind of make sense? So in order to do that, we're going to find the molar mass, and then we will take the, let me see how I want to word this. We want to divide the molar mass of the molecular formula by the molar mass of the empirical. Okay, so that should give us a whole number. Okay, so if we have, we'll just look at an example here, but it should give us a whole number, and then we can distribute that ratio throughout our empirical formula. Okay, so go ahead and turn your example page to the back here. Okay, let's go ahead and start with that first example on the back. Okay, the empirical formula is CH2O. So we need to find the molar mass of that empirical formula first. Okay, so 12 plus 2 plus 16 gives us a molar mass of 30 grams per mole for that smallest ratio. Okay, so if I want to find basically at what magnitude did I increase the size of this formula, I'm going to take the molar mass of the molecular formula, which was given, 180 grams per mole, and I want to divide that by the empirical molar mass, okay, which gives us 6. So we increased this molecule 6 times over, which means we're going to take that 6 and we're going to distribute it to this compound, CH2O, which gives us a molecular formula of C6H12O6. Okay, we still see our ratios as 1, 2 to 1. Okay, so the ratio of those elements did not change. The percent composition would still be the same. But we've just got a bigger and bigger version of that molecule. Okay, would this be considered a molecular formula of this same compound? Yeah, right? It's still 1 to 2 to 1. Okay, do we see how that works? So there's one empirical formula, but there might be a lot of molecular formulas. Okay, does that make sense? Empirical is always the smallest ratio of those elements combined. Okay. Questions here? All right, let's just look at a few here. I want you to determine, are they empirical formulas or molecular formulas? So this is not on your sheet. This is just something separate. Okay, you don't even have to write these down. I just want you to look at them. Okay, is this compound right here a molecular or an empirical formula?
Empirical.
Empirical. This one?
No, the molecular.
This is a molecular formula, right? This is not the most reduced version. So what would the empirical formula of this compound be? CH. Good. So the empirical formula here would be CH. Okay, does that make sense? All right, what about this compound? Empirical or molecular? Molecular. So what would the empirical formula here be? CH2. Okay. This one, empirical or molecular? Empirical. And empirical or molecular? Molecular. And what would the empirical formula be? CH4. Okay, CH4. Okay. Questions? All right, let's go ahead and try the last one here on your sheet. Now you have to find the empirical formula first, and then take it a step farther and look at the molecular formula. So this one combines both skills into one. Okay, so again, you can try it on your own. I'm going to work it up on the board if you get stuck.